The paper, Heteroskedastic Geospatial Tracking with Distributed Camera Networks, introduces a novel approach to geospatial object tracking using a distributed camera network. This approach aims to detect and localize objects as they move through a scene, predicting an object's track in geospatial coordinates along with uncertainty over the location. The author's work is motivated by the increasing use of IoT devices in smart cities, particularly for traffic monitoring and pedestrian safety. The paper begins by discussing related work on tracking, including model architectures, multiview computer vision, and probabilistic tracking. It highlights the limitations of traditional tracking benchmarks that assume access to high-quality video data and focuses on the multiview geospatial tracking problem. The authors then introduce their custom dataset, which includes high-accuracy ground truth object locations collected at 100 samples per second using a motion capture system, combined with video from 4 camera nodes with different partially overlapping views of the environment. This dataset spans multiple scenarios, including an open environment and an environment with occluding structures, as well as normal and low lighting scenarios. The authors present a modeling framework for addressing this task, which involves augmenting neural network object detection backbones with adapters that translate within image features into geospatial coordinates with associated uncertainty. They explore how uncertainty calibration and fine-tuning through a differentiable tracker affect performance. The authors experiment with both existing and custom backbones within the HGDs and assess the impact of geospatial detection calibration and fine-tuning on tracking performance. The paper concludes with a discussion of results, showing that recalibrating the output of the HGD models using an affine transformation of their raw covariance outputs can significantly improve the log likelihood of true object locations. Fine-tuning by backpropagating through the Kalman filter further improves performance for most HGD models. The authors also demonstrate that their custom HGD backbone can provide performance on par with ResNet 50 and DITR backbones under normal lighting conditions while simultaneously providing significant improvements in runtime latency. Interestingly, they show that in the low-light condition, the DETRBASED model has remarkably more robust performance than the other models considered. The research paper also discusses the development of a heteroskedastic geospatial tracking model framework for object tracking in various scenarios. The framework consists of heteroskedastic geospatial detection (HGD) models and a geospatial tracker (GST) based on a multi-observation Kalman filter. The HGD models predict a full covariance normal distribution over the location of the object in geospatial coordinates, while the GST component filters these predictions to generate smoother trajectories. The framework is tested using 3 backbone models: ResNet 50, DITR, and a custom model. The custom model is found to be the fastest, with a runtime analysis showing it to be 6 times faster than DITR and 2.5 times faster than ResNet 50. The paper also includes details on data collection, including scenarios with open and occluded environments, and data preprocessing techniques. In the proposed research, the authors focus on the geospatial object tracking problem using data from a distributed camera network. Their goal is to predict an object's track in geospatial coordinates along with uncertainty over the object's location. They have presented a novel single-object geospatial tracking dataset that includes high-accuracy ground truth object locations and video data from a network of 4 cameras captured under normal and low light conditions. The authors present a modeling framework for addressing this task, leveraging a multi-observation Kalman filter-based tracker in conjunction with a set of independent heteroskedastic geospatial detection models. This framework is specifically motivated by a communication-constrained version of the tracking problem where it is too expensive to centralize raw image data, and thus late fusion of low-dimensional representations is required. The authors evaluate the performance of their HGD model using various metrics, including negative log likelihood, NLL, object probability mass, OPM, detection recall and precision, DET-PR, and location accuracy, LOCA. They also experiment with the effect of Kalman filtering, comparing the average performance of 4 HGD models to the performance of the baseline Kalman filter model. The authors present baseline performance results for both normal light and low light data scenarios, using 3 backbone models: ResNet 50, DETR, and their custom model. The results show that the DETR backbone achieves better NLL in the low light setting and outperforms the other backbones in terms of OPM and tracking metrics. The authors also experiment with Kalman filter fine-tuning, which results in an improvement in their custom model on both data scenarios. After calibrating and training through the Kalman filter, the author's custom model is able to achieve better NLL score than DETR in the normal light scenario at 6 times lower latency. It is also able to close to within 0.5 nats of the performance achieved by the ResNet 50 backbone in the normal light scenario at 2.5 times lower latency. Here is the combined summary. The paper provides a comprehensive overview of multi-object tracking, emphasizing the limitations of traditional computer vision techniques and the need for novel approaches. It introduces transformer models, which have shown promising results in various domains, and explains their adaptation for multi-object tracking tasks, leveraging their ability to capture long-range dependencies and contextual information. Several state-of-the-art transformer-based methods for multi-object tracking are reviewed, including TrackFormer, Motor, and DETR3D. These approaches integrate transformer layers differently, such as using them as feature extractors or incorporating them into the loss function. The paper discusses the technical details of these methods, including their architectures and performance metrics. However, the authors also address the challenges associated with applying transformer models to real-world scenarios, including computational efficiency, data requirements, and model interpretability. Despite these challenges, the paper highlights the potential benefits of integrating transformer models into multi-object tracking systems, particularly in improving accuracy and robustness in complex environments. The authors emphasize the need for further research to overcome the challenges and ensure widespread adoption of transformer-based multi-object tracking techniques. This includes exploring strategies to improve computational efficiency, reduce data requirements, and enhance model interpretability. By acknowledging both the opportunities and challenges in this rapidly evolving field, the paper presents a thorough analysis of the current state of transformer-based multi-object tracking.